Okay, welcome back to this course of stereochemistry. In the last lectures, what we have introduced to you is the concept of chirality and stereoisomerism. We have seen that there are molecules which have the same constitution, same molecular formula, but they can be different, and the relationship between these molecules are known as stereoisomerism. Okay. Now, stereoisomerism, we have seen that they are of two types. On one side there is this enantiomerism and the other side is the diastereomerism, or you can say that the stereoisomers are classified into enantiomers and diastereomers. What are enantiomers? Enantiomers are the non-superimposable mirror images of each other. Okay. Molecules which are non-superimposable mirror images are called enantiomers, and they have the ability to rotate the plane of plane polarized light, either in a clockwise fashion or in an anti-clockwise fashion. Now, regarding the other class, that is the diastereomers are not mirror images of each other, but they have the same molecular formula, they have the same constitution, only the steric disposition of the groups in space are different. Okay. So, what about the rotation of diastereomers? Now, diastereomers also can have rotations, they can also have rotations. So, they can also be chiral. Okay. Only thing is that diastereomers are not connected by the mirror image relationship. If a molecule, we know also that the condition for chirality is that it is the absence of certain elements of symmetry which makes a molecule chiral. We just revisit quickly what are those elements of symmetry. A molecule is chiral when there is no I, that is means center of symmetry or the inversion point present, there is no sigma, that is the plane of symmetry which is not present, and the alternating axis of symmetry which is denoted as S n, that should also not be present. Okay. So, a molecule devoid of I, sigma and S n will be chiral, and this there is another term which was earlier used, was that the molecules which lack these three elements of symmetry are called disymmetric molecules. And we went a step ahead little bit, because we know that I is equated to S 2, that means, whenever a molecule has I, a center of symmetry, the molecule is bound to have a two-fold alternating axis of symmetry, and whenever there is a plane of symmetry present in a molecule, the molecule must have an S 1 axis. So, one-fold alternating axis of symmetry. So, it will be sufficient to say that the minimum condition for chirality is the absence of S n axis, okay, where n could be 1, n could be 2, or n could be any other number. Okay. But for you students at this stage, I think I will say that you better mention all these together, that first you tell that the molecule should be disymmetric. So, it should be devoid of I, sigma and S n, and since I is equated to S 2 and sigma is equated to S 1. So, it is sufficient to say that a molecule becomes chiral when it is devoid of an alternating axis of symmetry. Okay. Now, let us come to this molecule which show chirality. Okay. Chiral molecules are those which, as we have said, that are those which can have a mirror image which is not superimposable on it. That means, it shows a non-superimposable mirror image. Those molecules become chiral, and the condition of chirality we have just explained in terms of symmetry. Okay. Now, these chiral molecules have the ability to rotate the plane of plane polarized light, okay, and that is a characteristic of a chiral molecule. So, if you have a plane polarized light which is generated by what is called a polarizer. A polarizer could be made up of crystals, and it not all crystals, but certain particular type of crystals. So, when light passes through the crystal, it comes out as plane polarized light. okay, and the plane of polarization will depend on the what is called the principal section of the polarizer. Now, the polarizer can be, nowadays polarizers are also available in as sheets, as thin sheets, transparent sheets are also available as polarizers. So, what I am saying that it has got what is called a principal section, and this principal section, this plane of plane polarized light is actually coaxial with the principal section. But without getting into the very intricate details, you can understand it simply by thinking that there is a slit in the plate, and when light is passing through it, so only the vibrations which take place along this the axis, they will pass through, and so the vibrations are all now are aligned to this slit, the slit, and so that is the plane polarized light. Now, this plane polarized light, if it passes through a molecule in a solution, if the molecule is liquid, then it is okay. If it passes through a molecule which is a liquid or in a solution kept in a what is called a cell, then this plane polarized light will interact with the molecule, and ultimately if the molecule is not chiral, so the plane of plane polarization, the plane of polarization of the plane polarized light, that remain coaxial, that means the plane does not change, the plane does not rotate, that remain coaxial with the slit, which is actually also called the principal section of the polarizer. Okay. Now, how do you know that the plane has not rotated? So, you actually place another sheet which also have the ability to produce polarized light, but this is used as, because this is used to analyze whether there is any rotation in the plane of polarization, this is called an analyzer now. And if the principal section, that means if we have simplified it as just like having a slit in the middle. So, if light comes and if this slit, which is the principal section, again I repeat, that is coaxial with this, and if there is no rotation in the plane of plane polarized light after passing through these molecules, then what happens? Light will pass through with the same intensity. So, there will be no decrease of intensity, so it will pass through. But if there is a rotation of the plane of plane polarized light, then what will happen? This will not remain like this, the plane of polarization will now change, the plane will change, and if the plane changes, so what happens? Some of the light, so the light cannot pass through, all the lights cannot pass through some, so the light will become diminished as it, if you make it coaxial, these two axes are remaining in the same direction. So, to have so some of the light will be partly cut out. To get the maximum intensity, what you have to do? You have to rotate it, and you have to rotate it in this direction like this, so that this slit or the principal section, that becomes now coaxial with the rotated light, which has been rotated by the molecule that was in the cell. Okay. So, this amount of how much you are rotating, that gives you the amount of rotation that these molecules have done to the plane of plane polarized light. Okay. Another thing, so this is one way to know whether the molecule is chiral first of all, and then how much is the rotation that it is introducing into the plane of plane polarized light. Okay. If you suppose this is not rotated, suppose this remain the same, this molecule is not chiral, so it will not rotate the plane of plane polarized light. So, now the full intensity of light will come out from this side. if you now rotate it by 90 degrees and make it orthogonal, the axis, this slit is now orthogonal to this slit. So, what will happen? All the light, because it is perfectly perpendicular. So, all the light will be cut out and it will be no light will pass through. No light will pass through. If suppose this gets rotated, so if the molecule is chiral, so this gets rotated. So, now this is no longer orthogonal to the plane of plane polarized light, because it got rotated. So, in order to cut off the entire light, so what we have to do, we have to rotate this and rotate this in this direction. So, that the slit now becomes orthogonal. So, the slit now becomes orthogonal to the plane of polarization. So, there are two ways to. So, now the amount of rotation that you need to cut off the light is again the amount of rotation that is induced into the plane polarized light by these molecules. Okay. So, there are two ways, either you get the brightest light here, and then see how much rotation you have to do to bring the light to the brightest position, or you make it orthogonal, so that no light will pass through. Now, if there is a rotation, then you have to rotate this further, so that it becomes orthogonal to this plane of polarization, and this amount of rotation is, it will be the same as this. So, either you get the brightest field where all the light is passing through, or the other way around, you cut off the entire light. So, amount of rotation to cut off the entire light, or the amount of rotation to come back to the full brightness, is the rotation that has been induced by these molecules to the plane polarized light. Okay. Now, next is that on what factors this rotation depends. This rotation is obviously that will depend on the nature of the molecule, that is the first thing. If you different molecules have different capability to do the rotation, either to the right or to the either to the clockwise direction or to the anti-clockwise direction. Now, for a particular molecule, so the first thing is that it depends, it varies from molecule to molecule. The second thing is that if for a particular molecule, the rotation which is denoted as alpha, that is proportional to the concentration, to C. C is concentration of the compound in solution, of the chiral compound in solution. Okay. And it is also proportional to the path length. That means, this is your polarized light going through a solution of a compound. So, this is called the cell, the solution is kept here, and this is what is the length through which the light interacts with the solution. So, this is called the path length, and then it comes out. So, it depends, if you lengthen it, then also the amount of rotation will increase. If you make it concentrated, the amount of rotation will also increase. So, it is directly proportional to C and it is directly proportional to L. So, if you combine these, so alpha becomes a constant into C into L, and this constant is denoted by again alpha, but within a third bracket, and then alpha into C into L. This is what is called Biot's law. Okay. So, what is this constant, that alpha which is written in third bracket, that is called the specific rotation. Specific rotation. Okay. Now, this specific rotation is the intensive property and not the rotation. because the rotation will vary with concentration. If you take more concentrated solution, alpha will increase. If you take longer path length, alpha will increase, but the specific rotation is constant, provided, of course, there are other issues here, provided the wavelength of the light is fixed at a particular value, and also provided you carry the experiment at a particular temperature. Okay. So, this specific rotation is dependent on the wavelength of light that is used, and it is also dependent on the temperature that is also used for the measurement. Okay. Usually, we write this specific rotation as this denotes the wavelength. Now, d denotes the wavelength of light that comes out from the sodium lamp, and that is 589 nanometer, and this is T, that is denoted in degree centigrade. Normally we measure it at 25 degree centigrade, but if you measure it at other temperature, one should mention what is the temperature. Okay. I write here D is fixed because D is 589 nanometer. You do not have to write 589, you just write D, that is the wavelength of the sodium lamp, and this is the temperature. So, that will be is equal to the rotation that you observe by C into L. So, this is how you calculate the specific rotation. However, like specific resistance, you know, specific resistance is also very similar, that resistance is proportional to the diameter of the wire through which the current is passing and the length of the wire. So, ultimately you get a very similar sort of thing, that specific rotation is the specific resistance is the resistance divided by length and the diameter. Here it is divided by concentration and length. However, you have to fix the unit of concentration and the length, because in order to compare the values of alpha d, the specific rotation from compound to compound or for same compounds, if you want to compare the similarity of compounds, then you need to assign a unit for concentration and also a unit for length. Now, what is the standard procedure? The concentration is expressed in gram per milliliter and the length is expressed in decimeter. That is interesting, decimeter, not millimeter, not centimeter, but it is decimeter. Okay. So, again I repeat on what are the factors on which alpha d depends. Of course, it depends on the type of compound. Number 2, it depends on the wavelength of light that is used. It depends on the temperature. It also depends very slightly, but it depends on the solvent that is used for the measurement. Solvent also plays an important role in rotation, and the Beer's law is true only for little bit dilute solution. As you make it really concentrated, if the concentration is too high, then Beer's law also does not hold good. So, when you mention the alpha d, if you look at the books or if you look at the literature, you will see that the scientists are writing not only the specific rotation value, but they also write within bracket the concentration and the solvent. So, these have to be mentioned, that which solvent it has been measured and what is the concentration, whether it is 1 gram per milliliter or 5 gram per milliliter. So, the concentration should also be mentioned. This is required if you want to compare one substance with another substance. Okay. So, that is what is the specific rotation. And now, let us work out a problem, how to calculate the specific rotation. The specific rotation of a pure chiral molecule is will be the highest value that you can obtain. Suppose these are the pair of enantiomers, and suppose the left hand gives a rotation in the minus sense, that means levorotatory or the anti-clockwise, and this gives the rotation in the clockwise fashion. So, this is a dextrorotatory compound or the plus compound. Okay. Now, suppose this has a specific rotation of say plus 100 degree pure compound. Now, if I start mixing this left hand molecule into this system, then what will happen? The rotation will start decreasing, because you are mixing some of the minus molecules with the plus molecules. Okay. So, there are certain, so in a mixture of these two molecules, there may be different types of mixtures I can obtain from these two systems. First of all, I can have pure molecules separated, that is optically pure compounds we say. When we have a mixture, the question is what will be the, what is the ratio of these two? If the ratio is 1:1, that is 50-50, then there will be no rotation, because the amount of rotation it imparts into the plane polarized light is exactly equal in magnitude and opposite to what this left hand molecule is trying to do. Okay. So, the ultimately the resultant becomes 0. So, that is what is called a racemic mixture. But there are certain, there may be mixtures where this is present in 80%, this is present in 20%. And how do we know? How do we really measure the percentage of one enantiomer over the other in a mixture? Again I repeat, if it is pure molecule, that will match with the alpha D that is reported in the literature. If it is not the pure molecule, if it is 50-50 mixture, then there will be no rotation. So, these two cases are simple, but when there is some rotation, but which is not the actual alpha D value, then you have to calculate what is called the optical purity of the molecule, or what is called the enantiomeric excess of the molecule. So, you need to know the ratio of the two plus and minus compounds. So, a problem will solve this. Suppose we have taken an optically pure compound, and the amount taken was suppose 5 gram in 5 gram. Let us just check this problem, 5 gram in 10 milliliter. So, 10 milliliter of solution was taken, in which 5 gram of the optically pure chiral compound was dissolved, and suppose the path length is 100 millimeter. So, that means the cell through which it is passing, the cell has a length of 100 millimeter. So, what is the alpha D? The alpha, and the light used was suppose that D light of sodium D light. Okay. So, alpha D, and the measurement was taken at 25 degree centigrade. Okay. So, you just cite alpha D 25 will be equals to, what was the observed rotation, I did not say. Suppose the observed rotation when light passed through, the observed rotation is suppose plus 40 degree. So, then what will be alpha D? So, it will be alpha, that means 40, you put the sign plus, it is a dextrorotatory compound, and then divided by 5/10 into 100 millimeter is equal to 1 decimeter. So, since the unit is expressed, I said the unit of path length is decimeter. So, this is 1 decimeter. So, if you do that, it will come as plus 80 degree. So, the alpha D for this compound is plus 80 degree. Now, suppose now to this optically pure compound, suppose I denote it as plus A, and I mix x% of minus A to it, okay, x% of minus A to this mixture, and then I measure the alpha D value, and what I find that suppose the alpha D now of this mixture is plus 20 degree. So, now from this value we need to calculate what is the percentage of plus A in the mixture and what is the percentage of minus A in the mixture. Okay. So, we erase this because that is already done. Remember, the actual alpha D is plus 80 degree when it is optically pure. So, no minus A was mixed. So, optical purity, it is a new term. Optical purity actually gives from the optical purity you can calculate how much plus A is there, how much minus A is there. What is optical purity? Optical purity is the observed alpha D of the mixture, that means plus A mixed with some minus A, and the alpha D of pure compound. Okay. So, we know that both the values are, this is given plus 20. So, that will be 20 by 80, but it is usually expressed in percentage. So, into 100. So, that makes it 25%. Optical purity, by definition it is observed alpha D of the mixture divided by alpha D of pure compound. But what is the concept behind it? Alpha D has, this optical purity has a value 25%. It means that the rest 75% of the mixture is a racemic mixture. Rest 75 out of in the rest 75, 37.5 is the plus A and 37.5% is the minus A. Okay. So, optical purity is the excess that you have over the racemic pair, over the percentage of racemic pair, that is what is called percentage optical purity. Okay. That is also called the enantiomeric excess. That is also called the enantiomeric excess. Okay. Enantiomeric excess means, again I repeat, that means the amount, the excess amount that you have over the racemic amount. Okay. So, in this case optical purity or enantiomeric excess is 25%. Now, how to calculate how much plus A is there? Total plus A is 25 plus half of the remaining 75, that means 37.5. So, that makes it 62.5%. And what is the extent of minus A? That is the only 37.5. Okay. So, your x, the value of x here is 37.5. So, you have mixed 37.5% of minus A into this mixture. So, that gives you 25% optically pure material, or the enantiomeric excess of the mixture is 25%. Okay. Just to the other way around, suppose I say that in a mixture has 90% optically pure E, 90% optical pure plus A. That means the optical purity of the mixture is 90%, or the enantiomeric excess, which is written as E is 90%. Then calculate the percentage of A plus A, how much, and calculate the percentage of minus A, that is how much. So, you can easily calculate, because E is 90%, that means the 10% of it is the racemic mixture, because enantiomeric excess, as I said, is the excess over the racemic amount. So, the racemic amount is 10%, and out of this racemic amount 10%, 5% is plus A and 5% is minus A. So, this becomes 5% and this becomes 95%. Okay. So, that is the backward calculation. If optical purity or E is given, then you can calculate the percentage of plus A or minus A, or if you want to know the optical purity of a sample, we have to measure the alpha D, and then if the alpha D of the pure compound is known, then you can calculate the enantiomeric excess or the optical purity of the sample. Okay. Thank you.